report in software tools and technologies. So this is a course which no one really wanted to do over here. Neither did I, but well, it's kind of forced on us, and we just have to go through it. But yeah, so like what we have is like monthly reports. So we'll have to submit 4 reports. This is the first report that I have to submit, and it has some cool things. Like I won't lie, there are some pretty pictures and things over here, but let's just get into it. So first thing that they talked about is version control systems, which is Git. So VCS, it's a very important. So like version control is a part of software development, and it's like it allows for continuous integration. So like you have this kind of framework that developers will like commit changes into a source control server, right? So many times at projects you'll see this unstable release or things like that, or development repositories which are different from the stable repositories which are like actually used by everyone, right? And that's because these have to be different so that you can safely merge code, right? So the developers will commit their changes to a source control server, right? Then the client server, right? So this is the interface that clients use. It fetches the changes from that, like from time to time. Whenever the developers say like, okay, this is a stable version now, you can take the thing. So it takes that, right? It does a lot of tests on this thing. So like you might have these things called so it's like PyTest, there's a PyLint and all of these things. So these tests are run automatically through GitHub, and then when all of these tests pass, this is integrated into code base. So you would usually have maintainers for like different parts of the code base, and who will observe whether or not the code is actually functioning correctly, and then they will manually merge it, right, once all the tests are passing. So some features Git provides is like local repositories. It provides integration of that with remote repositories and all that. Pull requests, the usual. Like if you have been doing anything related to softwares, you probably know about GitHub. Now there's more. There's a thing called PyDriller. So it's a Python package that allows mining commits from GitHub. So it's used extensively for doing analysis of project and code base. So there's a lot of filters, options for querying. It uses Myers. So Git allows you to use 2 different algorithms. The Myers algorithm is what everyone used to use, but the histogram algorithm is the one which people should use for code, right? So yeah, histogram is really like what people should use. So let's even a report on that, like how different are different algorithms for diff, so or something like that. But yeah, so for every modified file in a commit, PyDriller provides us with this information. So it gives you so you can just look at the source code of PyDriller itself, and then you'll be sure of what's happening, because it changes with different versions. But it also gives you this nice thing called McCabe's cyclomatic complexity. So this is like this kind of tells you how complicated the program is and how many test cases you're going to need to debug the program correctly, right, to test it properly. So the coding effort is one other metric. So this is just like to get to a certain node, how many nodes that you have to go through in a syntax tree, right? So programming languages are first parsed in a compiler, and then a syntax tree is created, and then the node number of a particular node in the syntax tree tells you the amount of effort that you would have to put to get to that node and debug the thing, right? So that's another metric which people use, right? So for example, this might be a syntax tree, right? So this is from a programming language which I'm building. So it's just like a random stupid thing. Like this is just, it could be way worse. Like the Python AST module, like it gives you much more complicated trees sometimes. Okay, because it's a complicated language, right? And in my case, my language was pretty simple. So it just has this tree. So like program is like x equal to 8. If x is equal to 1, then you print 1. Otherwise, if x is equal to 2, you print 2. So how am I reading? I'm just going through the leaf nodes, right, in the topological order, and that tells me the program. Cool. So how is this related to software development? Well, you can use this to analyze how a project is like being developed real time, right? if it's a very large project, like let's say like Flask or maybe Sage Math or Gap or something like that, you would want your project to be constantly analyzed, right? Like if you're a very big company or something, you would kind of want that kind of analysis. So CFGs here mean a different thing. Here they do not mean context free grammars. Here they mean control flow graphs. So there's a model called Pi to CFG, which can convert your language, but more particularly the syntax tree, to a control flow graph, right? So using this, you can get the cyclomatic complexity, which is by the way different from coding effort. Coding effort is directly using the syntax tree, you find the node number. Here you are finding the number of different ways that you could run the program. And so basically this is the number of different regions that this planar graph partitions, the space into. So in this case, it's just one function, and this one function space is partitioned into 1, 2, 3, and so these ping blocks don't count, by the way. So it's just 1, 2. Okay, this is not even there. So it's 1, 2, and that's it. It's just 2. So this will just give me 2 as a complexity, right? Yeah, seems like. Okay, it's 3 apparently, because there's another loop. Sure, this is 1, this is 2. Where's the third one? Oh, okay, because this prints odd and then once again does x plus 2. So there's this region. Yeah. So it's actually 3. Cool. These pink things are just annoying, but I don't know. I'll have to put it because it's like these are system calls. So it gives you like 3 regions, this planar graph. So if you have read a bit of graph theory, you would know that the way to compute planar graph regions is to use Euler's formula. So it's just the number of edges minus number of nodes. So, okay, I'm gonna just refer to the formula directly. So it's number of edges minus number of nodes plus 2 times the number of disconnected components. So in this case, there's only one disconnected component, so it's just 1, right? So this makes it like this extra factor makes it like a linear thing. So like if you have 2 disconnected components, you add them together, that's the number of distinct regions that you would have, right? So P is the number of disconnected components. It's just a CFG. Sure. So remember this, kids. This is E minus V plus 2P. Or you can just say plus 2 because it's only going to be like one disconnected component. So it's E minus V plus 2. So it's essentially to remove bugs as early as possible. And since the more code you put, the harder it becomes. And so that's why you have to keep doing this sort of analysis. So at IITGN, some folks have built this thing called Minecraft. And it's not the game. It's not the Minecraft game. It's instead something which mines bugs from a repository. So for example, so there were already things like these before. There were things like Fix.js and Tufeno et al. And all these things. But this is one which is kind of language agnostic because it's using this thing called tree sitter parsing algorithm. So it like uses it's a website, right? Just go look at it. It parses all kinds of codes that you would ever need to parse. So it has that functionality that it is language agnostic. Then on top of that, sometimes you also want to like analyze what kind of bug are you dealing with, and so you have this thing called MineCpp, which is basically like Minecraft++, right? And this adds extra things like it adds like similarity scores between the buggy and resolved code. It adds more things. Okay, just more things, right? It adds like specific code context, precise code context you call it. So similarity score, test case indicated whether or not the fixed bug actually has a test case now, so that when it fails again you'll know, and things like that. So this is just like my work for lab 1. It's not important. It's just dealing with GitHub. It isn't too complicated. So we had to add a PyTest and PyLint. That's all. Then this is MineCpp, right? This is how MineCpp functions. Like it's the visualization that it creates, and it also creates these charts. I don't know if it's some script that I wrote, whatever. It creates these charts. So this is like a quantitative analysis of the repository. This is just for the last 10 changed files, right? This is for 100 rows, this is for 1000, this is for the full data set. So you see these spikes This is mainly because of changing import statements in different files, right? In the similarity course, you can see that the blue and crystal blue scores are kind of like 0.5, 0.4 low, pretty low, right? While for bird score, it's very close to 1. So if I had to, as a programmer, go with a score, I would probably go with blue and crystal blue, right? So this is just like a script, it doesn't really matter. None of this really matters. Yeah, okay, so this is the mismatches between the histogram and Myers algorithm for different kinds of files. And what you can, so this is just for the Flask repository, and what you can see is the highest percentage mismatches, they occur in the documentation type files, like text, markdown, all these things. And it's a weird thing, isn't it? Like, you wouldn't expect that sort of thing, because what, and this is including the fact that I removed spaces. Yeah, so it's not even accounting for all of that. So in source code, you won't have those sort of things, because spaces do not actually mean anything. But when it's text files, they do. Like if in markdown you miss a new line character, you could literally just go from a new paragraph to just editing in the same paragraph. So it really matters, right? So these sort of changes, right, mismatches within the algorithms, these happen a lot when you have non-source code files, right? Because what I think is like the histogram algorithm is more of a sort of a heuristic based algorithm, and so it doesn't really take into account whether or not like there's actually a match between the two things. It will actually put white spaces as changed things as well, so just be wary of that. So this was lab 4, I think, which was involved with what did we have to do in this lab? I forgot it. Yeah, I don't even remember it. It's gonna load. Fine. But yeah, so the reason nobody really likes this course is because none of it is it's actually going to be used like practically. It's still cool. You're making cool reports. That's enough. I think that's enough of a incentive to keep doing it, because the reports look cool. Yeah, so this, what was this exactly? What did I do over here? I kind of forgot. Yeah, it's gonna take a bit of time to load because there's a lot of so this was creating cyclomatic complexity graphs. So like for Flask, the app.py file has this cyclomatic graph complexity thing. So this is just finding the most edited files in Flask repository, and then for those it's generating these plots. Just how does the complexity of a code change, right? And you can really see that this does change. Like, so firstly, for the most changed file, it's just the app.py file, which actually has the main Flask class, and so it's a problem because it's a very big code and I cannot visualize it. And so instead I'm going to go to the second most changed thing, which is helpers.py. Yeah, so let me just load this real fast. Come on, load it. So yeah, the report is so big that it really like just takes time for this thing to load it, which is a problem, but whatever. Okay, did it get stuck or something? Maybe I should just open this in Chrome. Maybe then it will be better, because yeah. My OS is screaming at me right now, like, don't do this sort of thing to me. But it's okay. I'm gonna do this sort of thing to you. I'm a sadist. Anyway, so the CFG evolves like this. So it just killed all the numbers that I had labeled for different. That's a bad thing, but sure. So it was like this. Initially it was like this, then it changed and it became yeah, so we had another function added to it, didn't we? Yeah, so it became like this. So you had two new functions, methods, right? Okay, this was actually already there. You just changed the control flow a bit. So you have these two things now. Oh, so this is just that. Oh, you just added more code to it and you added another function, and then you added even more code to it. Yeah, so there's little to no change from here to there, except you can see this large function that you had, it changed. Like now it became this small thing, and then it grew even more because you added another function, I think. Yeah, so you have one, and then that's two, that's three. You just took all of this code, and so okay, this function actually maps to this one. And then you added another function over here, I see. So yeah, this is how it changes, and this one is definitely way more complicated. Like just by the size of this pink block, you can see that it's getting smaller, right? Here it was like large, slightly less large, smaller, and even more small. So the complexity is increasing. That's the point. So this is the side-by-side comparison of like commit 0 and 105. So this is commit 0, this thing is commit 105. So in the CFG evaluation, it does seem that the code complexity, although already high, is changing. So it increases from 80 at commit 0 to 120 after 105 commits. So when I say commit 0, I just mean like the newest 1000 commits that I've mined, right? So the CFG is rotated by this script, we don't really care about that, it's just Python CFG. So the conclusion is, there's no conclusion really. There's no, yeah, I just did all of this just to like make this report, that's it. Like there's no real learning from any of it. But some future improvements, one thing I noticed was that the LLM that Minecraft uses is shit. It does not actually generate any kind of sensible outputs. ChatGPT beats it, like by a very big margin. So they should really just use some pre-trained model, right? And they say that they don't have enough credits and all of that. Excuses. Right? You just want to use something that doesn't require money or things like that, because your work isn't all that good in the first place. But it's okay. I get it. Like baby steps. Get noticed first. Get some funding. Then you can use ChatGPT, and then it would actually be a very sensible thing. But yeah, so my reviews for Minecraft, for MineCPP. Well, Minecraft is a very good tool. MineCPP is trash, complete trash, because although it gives me a lot of analysis on what's going on in the code base, it does not actually help at all. It does not do what it was supposed to do. All it's giving me is just like pretty graphs. What am I supposed to do with it? Nothing. While Minecraft, on the other hand, it's like it mines the bugs, it tells me what bug pairs there are, it tells me the coding effort, it tells me complexity and all sorts of things. So don't use MineCPP, not right now at least. Wait for a while till it becomes mature enough to be usable. But yeah, so this is it. I'll see you guys in the next video.